Good evening once more. Today we'll be looking at effect size. And many a time when we run our analysis, we calculate a particular statistics where we are dealing with hypothesis testing. The end point is p-value. It is when we are dealing with confidence, we use confidence interval, which is another inferential method that when p-value, is a different thing. We all know that the p-value does not give much information. Apart from the fact that it's a probability, that the difference you have found is due to chance occurrence.
That's all.
So if you calculate and probability is so low, as less than what you set, most of the time we set 0.05, which is 5% as the level of significance. That is where the level at which we are going to reject no hypothesis. If it's so low as lower than 0.05, say, oh, that shows that the probability that is due to chance is so low, so minimal. Let's assume that it's not due to chance. The difference is significant. But if the probability is not bigger than what you have set, bigger than 0.05, we are saying that when the probability that something is due to chance is as high as that, anything from greater than 0.05 up to 1, it means that it's due to chance occurrence. The difference is not a true difference. Because if you do something, of course, you see, observe different. But it doesn't really mean that it's a good difference. Because if you do it again, you may get different things. That's just the logic. So the p-value just tells you whether it's significant or not. It's just a probability. And that is why people that advocate for the use of confidence interval instead, one of the arguments is that with confidence interval, you can know if it's significant also. You also have better information. You have true information in addition. And the first one is able to quantify the association. And that is part of what we are looking at also today, effect size. So you'll be able to give you tell you something about the effect size, and also give you a range of value within which you are 95% confident that you will find the population value. That is, you will find the parameter, because what you have calculated is statistic. But the real value is parameter. You don't know, in as much as you did not attend to all the elements in the population, your statistic can never be equal to the parameter. But if you attend to everything in the population, that shows that your statistic is equal to the parameter, because you have, if it is all the population you are attending to, that shows that you have calculated the parameter. But most of the time, for logistic reasons and many other things, we cannot attend to the whole population. We take a sample. So from what we get in the sample is a statistic. You can only give the confidence interval is just a broad estimate that, okay, since I'm not 100% sure, but I want to be 95% sure that the true value will be in between this and this. It's not even, you are not 95% sure that it's a particular value anyway. You are still 95% sure that the true value will be in between a range of value. Now, that one apart, what we are looking at today is to look at effect size. We have already known that significant, when it says statistical significance with p-value, does not mean much. One should be able to describe the result in terms of measure of magnitude. That is, you give a value, you're able to quantify it. The other time when we discuss measures of association, when we discuss odd ratio and relative risk, they are part of what we are discussing today, because they are part of the effect size. They are part of the measure of what you use to measure association, because it's able to quantify association. Not just does a significant difference exist, but how much difference exists. So it will tell you. So the effect size is to tell you how much difference. The p-value can tell you that there's a statistically significant difference. But it's the effect size that will say this is how much is the difference. Now, p-value is not enough. A lower p-value is sometimes interpreted as meaning there is stronger relationship between two variables. However, statistical significance means that it is unlikely that the null hypothesis is true, less than 5%. It's just probability. You just say, oh, if the p-value is small, it's unlikely that there is no difference. That's what it's saying. That is, it is likely that it's going to be different, since the probability is so low. A significant p-value tells us the association or a difference exists. Yes, you know that there is a difference, but you don't know the difference. The first size tells how much difference. So the first size is the one that quantifies the difference. It can be argued that emphasizing the size of effect promotes more scientific approach, though it's more scientific than just saying p-value significant. So if you talk about the first size, it's more scientific. So unlike significant tests, effect size is independent of sample size. You know, we have said it many times. If your sample size is very small, you may not see a particular significant, what is supposed to be significant may not be significant. You are not able to get it. Then we have talked about correlation, coefficient. It's part of what we're discussing, because it's part of the effect size, measure of the effect size. Correlation coefficient, you don't interpret it with p-value, it doesn't make sense, because whether it's going to be significant or not depends on the sample size. If the sample size is very large, a small correlation will be significant. If its sample size is very small, even a big correlation will not be significant. So can you see? So effect size does not depend on sample size. So p-value is out of it, especially when you are even interpreting correlation. So it's not only correlation, in many of those things that you have been using p-value, but you have the understanding of how it is better to use effect size to interpret your result. You'll be able to do better job. Meaning of effect size is a statistical concept that measures the strength of the relationship between two variables on a numerical scale. What we mean by numerical is able to quantify. When you say you quantify something, before you can quantify it to be on a numerical scale, you have to allot value. Oh, 1, 2, 3. That's the meaning of numerical scale. You're able to put number. Just like somebody say, he's old. How old? Unless you're able to tell that he's 80 years, he's 70 years. For us to know how old. Or is young. How young? Young is relative until you quantify how young or how old in terms of numerical value. For instance, if we have a data on the height of men and women, and we notice that on average men are taller than women, the difference between the height of men and the height of women is known as the effect size. The effect, the difference. The p-value will tell you is significant, it is very significant. We want to know how much difference between men and women when it comes to height, averagely. The greater the effect size, the greater the height, the difference between men and women will be. Statistic effect size help us in determining if the difference is real or if it's due to chance, change or factor rather. In hypothesis testing, effect size, power sample size, critical signal level are related to each other. Somehow they are related. In meta-analysis, effect size is concerned with different studies and then combine all the study into simple analysis. Because many a time, why I made mention of I said the last sentence, is because many times only in meta-analysis that people even talk about effect size. Because people don't usually talk about effect size when they do the study. And because of that, even in many articles, people don't report it. Journal, you will not see it. Even many statistical packages, they will not run it out. They will not make provision for calculating the effect size. Most of the effects I go to see that the statistical package, they don't calculate. Because those people that develop the packages, they are business people. It's worth people demand, what they do is they respond to the requests of their customers and what they ask them to do. So they don't just do something because they want to do it, or they want to put something because they know. They do their market survey, they get response to their customer to do. By the time people start demanding, then you see that they will put it there. Now, how do we calculate the first size or measure the first size? There are different ways, and the commonest one you see. So many people propose many ways, but sometimes if you will include all of them, it will be tantamount to repetition. I'm going to tell you that later, when as we discuss, you mention of something like that, because there's something that some people propose to be a first size. But you can see that some other things are already doing the work. Now, I have 5 classes here. Correlation coefficient on its own is an first size. Remember when we're discussing correlation, the origin of correlation, when Pearson described correlation from covariance, although the first person to coin the word correlation was Francis Galton. Francis Galton was teacher to Carl Pearson, and Galton was a geneticist, many things, geographers, anthropologists. You know, he was many things. Because he was a philosopher, was cousin to Charles Darwin, person that proposed evolution theory. He borrowed the word from biology, correlation, trying to talk about species that are related. You know, it's a word in biology, they are related species. Correlation was the first person to coin the word correlation, but the student can persist through the work further. Was able to describe Pearson correlation coefficient. Now, we have discussed correlation before. Pearson, the coefficient, the measure, Pearson, Spearman, Kendall. Then standardized mean different. There are many ways, many people describe. I think Coren was the first to describe polycurrent D. We're going to look at all of them. Glass tried to modify current work. Aegis also tried to modify current work. So somehow they just try to tweak it to them to make it better. Then on coefficient of determination, when we talk about regression, linear regression, we talk about that coefficient R squared. And you'll be surprised. And it's related to correlation. I think just with that correlation, because it's not because correlation coefficient, but of course, for Pearson correlation, coefficient of the denomination is Pearson's correlation square. But what we have is not actually the coefficient of it's actually the coefficient of determination, the ratio of the coefficient of determination and coefficient of non-determination. We'll discuss that. Then Cramer's method, this method and the 1, 2, 3 method, they are pointing towards quantitative outcome. Where apart from under correlation also, even though there are some things that are categorical for Spearman and Kendall, they are actually categorical in a rank form, which you cannot give from quantitative value. But majorly, you can say 1, 2, 3 are addressing quantitative outcome, while Cramer's number 4 and 5 categorical outcome. I'm going to discuss when you use one, when it's better to use the other. So under the Cramer's method, Cramer's 5, Cramer's V, then ratio, relative risk, odd ratio, and hazard ratio. Those are. So let's start unpacking each of them. Let's look at the correlation coefficient. We know that when we discuss correlation, it's a measure of degree of linear association between two variables. The value vary between or from -1 to +1. That can be anything from -1 to +1. But that is the global description. But still, I still believe that it is better to say it's very from 0 to 1. It can be in positive direction or negative direction, but whichever way. So you cannot have a value that is greater than 1, either in the negative direction or positive direction. That is, it cannot be less than -1, it cannot be greater than 1. That's what it means. And the different types we have is in our slide, is in our videos, in our module. Basic correlation. This is the formula for, this one now. We will not talk much about what we are on their own. We have described them. They are on their own. Effect size. You don't need to calculate anything from them. Once you are calculated, you are not using them to calculate effect size. No, they are a measure of effect size. Is it Pearson, Spearman, or Kendall? And I put the notation here. You see that I put the formula for the 3, but the last 2, the point by serial correlation and biserial correlation, actually it's the same calculation with Pearson. Because you are running it with the software will give you under the Pearson, it help you calculate the biserial and point biserial. So what I just want to is the interpretation. You know that it's from anything from 0 to 1, either positive or negative. When it is negative, it means that the association is in opposite direction. If one increase, the other one decrease. That one. So when you see X and Y in the formula, X just means one variable, Y means the other variable. So if I've given an example before, if for example, Charles' law that talk about the volume and the pressure and temperature of gas, temperature and pressure, they are directly proportional. They increase as temperature increases, pressure increases. As temperature decreases, pressure decreases. That is direct proportion. That is positive correlation. It's a positive correlation in the sense that as one increase, the other one increase in the same direction. As one change, they change in the same direction. If one increase, the other one increase. If one decrease, the other one decrease. That is positive correlation. But there are some situations where it is in opposite direction, like in Charles Boyle's law. Boyle's law talk about the volume and pressure of gas. They are inversely proportional. As you increase volume, pressure decreases. As you decrease volume, pressure increases. So that is inverse proportion. That is negative correlation. So in mathematics, they call it direct and inverse. But in statistics that borrow from mathematics, call it positive and negative correlation. They say the same thing. You know that statistics, the branch of mathematics, there is on its own in the sense that it's the technology of scientific method. So there's no research you do anywhere on planet Earth that will not involve statistics, at least quantitative research. So in any field, it will involve statistics. So statistics is the technology of scientific method. Even though those people that develop it over time were those people that need it most. Biological scientists and social scientists were the people that developed statistics over the years. And the value, when you have something less than 2, is 0.2, no, it's from can be 0 to 1, either positive or negative. So it's 0.2. When we talk about, we didn't put sign at 0.2, less than 0.2, we are talking about either minus or positive. Negligible relationship, 0.2 to 0.4, low relationship, 0.4 to 0.7, moderate relationship, 0.7 to 0.9, high relationship, then high, very high relationship, greater than that. Sometimes they say 1 perfect. I don't know any perfect correlation, but I don't know if you can call it perfect relationship. Okay, we have talked about correlation coefficient as on their own, on its own, it's a measure of effect size. Standardized mean different. Thus, when you can, let me just this. Why do they say standardized? You have mean difference. You have standardized. If you just say mean difference, imagine you talk about blood sugar between two people, either male, between male and male, female, or rural and urban. The mean difference you get will be dependent on the scale you are using of your blood sugar. You say maybe in the among men 60, among women 65 milligram per day. The mean difference here is 5 milligram per day. But when you are talking of distance travel, somebody cover 250 kilometers, and that person cover 200 kilometers. It means maybe average distance they cover per day. So the mean difference would be 50 kilometers. So you see that, look at that one 5, this one 5. So it depends on unit and the value. So it's not universal. So if you are going to use for different variable, it gives you even different feet, the same feet, different variable, give you different things. So intelligent people have a way of circumventing that is by dividing that difference by the standard deviation. Because the difference carries the same unit of the original value, the standard deviation also carries the same unit. And when you divide two things of the same unit, it's unitless. Now become a ratio, and it's a universal thing. So the difference, mean difference divided by the standard deviation. That's why I call it standardized difference. So when a research study is based on the population mean and standard deviation, then the following method is used to know the first size. So look at the other standard difference. That's why we have the current, the current formula now. If you are dealing with population mean and standard deviation, just say the first size will be mu1 minus mu2. Mu is notation for population mean. It's for parameter because population mean is a parameter. So mu1, mu minus mu2 mean that two different populations over the standard deviation. Combined standard deviation of the population. The first size of the population can be known by dividing the two population mean different by their standard deviation. Current effect size. Current D is known as the difference between of two population mean and is divided by the standard deviation from the data. So the other one just more like the first one, it look more like hypothetical because most of the time you don't even know the population standard deviation. You don't even know, sometimes you know the mean, you may not know the standard deviation, you may not even know the mean of the population. So those people now come, okay, let's use what we have. So when you are dealing with the sample now, okay, D is the same concept. The mean different. This mean of group 1, mean of group 2, you remove it, divided by standard deviation. It's absolutely different. Actually, you are not going to produce minus there because it is different. If it is the second one, the one that is biggest will be the number 1. You see, X1 will be the bigger one because it's absolutely different. So the difference between them divided by the standard deviation. Where S, which is standard deviation, can calculate it. So it's a pool standard deviation and pool. That is for the 2, you put the standard deviation for the 2. This is the formula for the pool. That is, you calculate one standard deviation from the 2 standard deviation because each of them has its own standard deviation. So the standard deviation is a pool one, and this is the formula for calculating it. Then glass also came with its own. It's a free word. You can come if you have superior argument, usually have his way. So he has many intelligent come with different things. Glass also came. This method is similar to current method, but in this method, standard deviation is used for the second group. You use the standard deviation for the second group. So we're likely to get something close. Then edges also with its own method, the same thing. This method is the modified method of Cohen's D method. Edges method of the first side can be written mathematically as this, where standard deviation can be calculated using this formula. This one also is another way, is the same pool, almost pool standard deviation, but in another way, where is introduce something else. So it divided by the degree of freedom rather than by the total sample size. Yes, rather than the total sample size that this one did, it's divided by the degree of freedom because it remove -2. That is the degree of freedom. To make it more accurate. So, but if you look at it, you get the same thing. Yes, okay, this one is the one I now put under coefficient of determination. Sorry, this Cohen F square method is the coefficient of determination. If you remember, when you are doing regression, so we look at the Cohen's method, measure the first time when we use Cohen F square method, measure the first time when we use method like ANOVA and regression, multiple regression. You know, ANOVA, we have said it many times, ANOVA and regression, they are the same thing. They are two faces of the same coin. Now, here, the R square is the correlation square. That R is correlation between the exposure and all the exposure and the outcome. And we know that R square, there are different way, another way you can calculate it. But it means the same thing. It's still the same thing. What it means is the proportion of the outcome variable that is accounted for by the exposure variable. That is the proportion of outcome variable that is due to the exposure, because it's not everything about the outcome that the exposure is doing. The exposure you are working with, you are using to predict the outcome. For example, now if you say blood sugar or blood pressure, salt intake. You don't only salt intake that if you say you want to determine somebody's blood pressure from salt intake, it's not only salt intake that determines blood pressure. There are many things. So the contribution, the percentage contribution by the salt intake will be the R square for that salt. So it is called coefficient of determination. The percentage change in the outcome variable that is due to change in the exposure variable. Then the percentage change in outcome variable that is not due to change in the exposure variable will be 1 minus R square. Because the web say 1 means 100% minus R square. If you express your R square in 100% in percentage, that will be 100 minus R square. But if you express the decimal, 1 minus R square. That is what that one actually means is the proportion that is not due to that outcome variable. And they call it the coefficient of non-determination. The other one is coefficient of determination. Yeah, this one is coefficient of non-determination. Of course, when you add the coefficient of determination and the coefficient of non-determination, it gives you the total 1 or 100%. So what Cohen now did here is to the R square, which is the coefficient of determination, over 1 minus R square, which is the coefficient of non-determination. What he says that if you really want to see the effect, you want to divide what the exposure can explain in the outcome by what it cannot explain. If it explains effect is much, very well. What it can explain should be far bigger than what it cannot explain, which serves as the denominator. So when you divide it, should be greater than 1. So that's just it. That what it can explain should be more than what it cannot explain. The bigger it is, the better it is. So that is measure. So it's different from coefficient of determination. And one of the things I was saying the other time was that there are many methods listed somewhere, but like now, some people listed the coefficient of determination itself. Because this one is not coefficient, it's the ratio of coefficient of determination to the coefficient of non-determination. Then if you put coefficient of determination itself, if you look at it, this one is better. So you cannot be using this one and put that one also. So this one is better. This one, because this one incorporates what it can explain and divided by what it cannot explain. Some people also talk about regression coefficient. We know that regression coefficient does not even make much, because it just, you can use it to predict the outcome. When you are satisfied that the R square is okay, that the fit is okay, that it has explained the data very well. If you cannot say with confidence that the model has explained the data, so the predictive value, the ability will be very small. If you are predicting using regression coefficient, it's just waste of time. So regression coefficient will not make meaning to be effect size, but this f square is more important than that. So where R square is square multiple correlation, yes, I've said it. How do you interpret all these effect size, first size? So we are talking about interpretation of correlation, so but all these standardized means different. How do you interpret? Courant in 1988 published his paper and recommend that effect size 0.2 and below, small effect. No, it's between, this is now, it's between, well, in this one, it's not like a correlation that is bounded, but this one is not actually bounded, but whenever it's 0.2 and below, say small size, 0.5 medium size effect, and 0.8 and above, large effect. And if you look at the picture, look at this graph, because you are looking at a difference between two groups. Imagine, look at the division of the two groups. Look at the overlap. Like when the first size is 0.2 now, small effect, overlap is 83. They overlap very well, so there's no much difference. The effect size is equal to 0.5, medium effect size, the overlap is 67%. The overlap is less, so the difference is a little bit wide. The effect size of 0.8, large effect size, overlap here is 53. We still have effect size of 0.2, so that the overlap is 19. But sometimes also, no, this is the effect size of 2 rather, not 0.2. It's effect size of 2. So the overlap, can you see, is very minimal. That's why there's a gap between them. Now, let's now look, we have looked at the correlation, the standardized mean difference. Let's quickly look at Cramer's method. Now we are dealing with categorical variables. Whenever you have a categorical variable, chi-square is the statistic of choice for determining association between two categorical variables. It was first described by a Swedish mathematician and statistician, Harald Cramer. That's why it is named after him. These are measures of strength of association between two categorical variables. Cramer's phi. No, I see you are calling fire. That's going to pronounce the Greek word, a Greek letter, phi. Cramer's phi use 2 by 2, or is used with, yes, it's used with 2 by 2 contingency table. So this one is only 2 by 2. 2 by 2 table. That is when you do your classification, is 2 by 2, 4 cells. That is degree of freedom is 1. So phi is calculated by taking the chi-square value and dividing it by the sample size, then taking the square root. So square root of chi-square over sample size. That is We divide chi-square by sample size and now calculate the square root. So this is Kramer phi, this is the Greek theta phi, this is chi-square, and this is sample size. Very simple. Now, we also have Kramer's V. It's an extension of Kramer's phi. No, we said Kramer's phi is for 2 by 2 table. In situation when you have more than 2 by 2 contingency, so Kramer's V is preferred to phi because the value of phi may not be lie between 0 and 1. It can go below, above 1. Because normally it still lie between 0 and 1. But if the contingency table is more than 2 by 2, with that formula, because the chi-square may be greater than the sample size. Once the chi-square, which is the numerator, is greater than the denominator, which is sample size, it will give you value, it may give you value, it may, because you are still finding a square root. But if it's so much, it may give you the value that is less than, that is greater than 1. And it's supposed to be 0 from 0 to 1. So, no intelligent people have a way of circumventing that problem. So that is why the Kramers also still came with another modification. So what it does is to also put the degree of freedom there. Apart from dividing by the sample size, the degree of freedom, which is the row minus 1 times column minus 1. So in that case, it will a little bit jack up the numerator so that the denominator will not be greater than the jack of the denominator, so that the numerator will not be greater than the denominator. Because it is when the numerator is greater than the denominator that you will have something greater than 1. So Kramer's V statistic is a symmetrical measure, in the sense that it does not matter what variable is placed in the row and what variable is the color. It's symmetrical. Just like when you do your chi-square, chi-square is symmetrical because it doesn't really matter which one is row or column. The row or column and the way you do it affect your interpretation, but it doesn't affect the value of chi-square you are calculating. Whether this is row, whether this is a column, doesn't affect it. But it affects your interpretation. So it's a symmetrical measure. So it affects your interpretation. I'm talking of the interpretation of your table's percentage, but it doesn't affect the chi-square you are calculating and the Kramer's V you are calculating from it. So note for 2 by 2 table, Kramer's phi and Kramer's V are the same. Of course, now, if it is 2 by 2 table, now the degree of freedom will be 1. Yeah, this one will become like the other one. So the degree of freedom is 1, it will be the same thing, chi-square over square root of chi-square over n. How do you interpret this Kramer's phi and V? Please, you can be chatting your question. Chi-square says that there is significant relationship between variables, but it does not say just how significant and important this is. So Kramer phi and V is more like post-test to give additional information after you have done your chi-square. So Kramer's phi and V lie between 0 and 1, as I've said. 0 means lead to association between variable. That is when it's close to 0. If it is 0, no, there's no association. If it is as it's close to 0, it means that it leads to association. As you are close to 1, it means that the association is strong. The last set, which are the ratios. You see that for correlation for these ratios is what you know, the way you calculate them, they are being used as the first side. You can see that it's those other one that Kramer that you are calculating something from chi-square, or the other one current that you are calculating something from what existed before. But this one, the measure of association here, ratio on themselves, on their own, they are effect sizes. And in this category, we have odds ratio, relative risk and hazard ratio. Odds ratio is the same thing as relative odds. You can call it relative odds ratio because you are comparing two ratio odds rather. When you say ratio, you are comparing two things by dividing them. Two things similar thing, two things of the same unit by dividing them. That is ratio. When you say odds now, you are comparing two odds by dividing it. That's why you call it relative odd or odd ratio. The ratio of the odds of exposure group with the event of interest with the age odds of exposure in the group without the event of interest. What it means? If maybe somebody have lung cancer, what is the odds that he smoked before? If he's smoking and lung cancer, you have studied. Is smoking a risk factor, lung cancer? So the event of interest is having lung cancer. If the event is there, if there's no event, no lung cancer. So the odds, if you calculate the odds of smoking among the people that have lung cancer, and also calculate the odds of smoking among people that don't have lung cancer, when you divide it, you pick the one that is for the people that have lung cancer as the numerator, and the other one as the denominator. That is odds ratio. It's different from risk ratio or relative risk. So risk ratio also cannot be called relative risk. Though relative risk can also be called risk ratio. Because what is commonly known is that relative risk odds ratio. Relative risk also is relative odds. Odds ratio also is relative relative risk also is risk ratio, while odds ratio also relative odds. The ratio of the risk, relative risk now, the ratio of the risk of the event of interest in the exposed group to the risk of the event of interest not exposed group. If I still use the same lung cancer and smoking, here now you are saying, okay, among smokers, how many develop lung cancer? That is the risk of lung cancer. How many develop lung cancer over total of the smokers? How many develop lung cancer over the total of non-smokers? Those two risks, if you divide it, you put the one among the smoker over the one among the non-smoker. That is relative risk. You see, a calculating risk directly. You know how many people develop lung cancer among the exposed. But in the odds, you are starting with the lung cancer itself. How many people? What is the odds of smoking? Why you say what is the odds of smoking? You cannot say what is the probability of smoking because the event has occurred. All has developed lung cancer. Calculating the probability, if he has smoked, he will have smoked past in the past. Because if smoking is causing lung cancer, before lung cancer comes, he will have done the smoking. So you cannot calculate probability of something that passed. So you now calculate the odds. Of course, you see use the probability that, probability that he smoked the past over the probability that he didn't smoke. That's the odds. So odds of smoking among the people that have lung cancer divided by odds of smoking among the people that don't have lung cancer. Now, relative risk, odds ratio is a proxy to relative risk. In the sense that the real thing you want to measure is the risk. But because you cannot measure risk for that time because the event has occurred, you don't do odds ratio. Both of them, they are effect size. But we have discussed the relationship between them before in our measure of association, where we say that once the risk is above 1, the value of odds ratio is greater than relative risk. If the risk is below 1, the value of odds ratio is less than relative risk. We have discussed it. And there's a problem you can convert it from odds ratio to relative risk. So in this issue of odds ratio relative is for 2 by 2 table. You should know this is the formula for relative risk and for odds ratio, which we have done before. It's just to remind us that they are actually their measure of their effect size also. Now the last one is the hazard ratio. So in hazard, the difference between all of them are ratio now. The difference between odds ratio, relatively, and hazard ratio is that. Well, let me say the difference between hazard ratio and relative risk. It's actually will have been the same debate. This one is a rate because it's time. It has time element. It's rate of event. Because it's not just that the event happen. How often? What is the rate? Which one will be likely to occur first or more frequently? So the rate of event among the exposed. So the rate of event among the not exposed. So event rate among the exposed divided by event rate among the not exposed. So you see the distribution. This one is the event rate in the exposed group over the event, well, yes, over the event rate where the event, where is the event, occurrence of the event, not rate per se, in writing this one. Event among the exposed, then expected, that is the number of the event among the exposed, then the expected number among the exposed. Well, is event rate among the exposed, the expected rate. What really happened, the expected divided by the expected rate among the exposed. That is the hazard for the exposed. So the other one, event rate in the exposed over the expected event rate among event rates among the non-exposed. That is hazard among the non-exposed. So the hazard among the exposed divided by the hazard among the exposed is the hazard ratio. And how do you interpret hazard? All of the ratio, all of them, either hazard ratio or whatever, all the ratio. We know that when you write two things, if it is the rate, the thing is different, numerator and denominator are the same, it will be one. So one means there is no association. The risk is present among the exposed and non-exposed in the same way. So that is one. If it is less than one, or if it is greater than one, let's go. Or if it is less than one, it means that among the exposed, the risk is less, because that's why it's less than one. Because when you divide two things and it's not less than one, that shows that the numerator was smaller than the denominator. So if the risk is smaller among the exposed, the value will be, the ratio will be less than one. But if this risk is higher among the exposed, the ratio will be greater than one. And further, because you interpret it with confidence interval. We already said it before. When it crosses one, when the confidence interval crosses one, it means that it's not significant. Like this two scenario now, the one that cross, this number 2 and number 3. This one, the event rate is less than 1. Look at 1. But the confidence interval reaches 1, from less than 1 to above 1. By giving you that value, it's telling you that 1 is one of the value it can be in the population. So it can be from here to here, and 1 is one of them. And we already know that if it is 1, it means that there's no association, so no effect. No effect. So the same thing with this one. This one, the risk is higher than 1, but the confidence interval also is from less than 1 to plus 1, 30 after 1. 1 is one of the values in the population. In that case, it's not significant. It's only the first and the last that are significant. This first, the risk is less than 1. It means that The people that are exposed are less likely. Exposure is protective and is significant. And this other one, the last one, it shows that the exposure is causing it. It's causative and it's significant. I think we have talked about it before, and it's in our slide in our material there. I think we stop here so that we entertain questions. Yes, I can see some charts. Somebody says, sir, in very simple terms, what is the definition for degree of freedom? Then, simple term, well, something you say simple may not be as simple as that, but the definition of degree of freedom is the number of entity that is free to vary among the total entity. When you have 30 entities, how many free to vary is valid? When you have 12, how many is free to vary is valid? And the degree of freedom is the number of entity minus 1. So that's why, since you say simple description, that's the simplest. And you need to unpack the entity now. Because in some situations, the entity may be number of category. The entity may be number of subjects. The entity may be number of group. Can you see now? So those are the things. So this class now is not for degree of freedom. In fact, we have classes, the video is there. Go and subscribe and watch the video and get the material. You know, talk majorly on the whole day was on degree of freedom. So don't let us go and be doing that now. Now, another question, what is the difference between correlation and point by serial correlation? No, correlation, point by serial correlation is a form of correlation coefficient. It's an example of correlation coefficient. Just like we have Pearson, we have Spearman, we have Hendon, we have biserial, we have point biserial. But the issue there is that one thing that is unique about biserial and point biserial is that it's the same logic with the Pearson. So it's actually that Pearson, but the only thing there is that instead of a continuous variable being the second variable, is a dichotomous variable, which we code 1 and 0. So for point biserial correlation, the dichotomous variable has no underlying continuous. It was not from a continuous variable before. That's what it means. Like dead or alive, male or female. But for biserial, not point by biserial correlation, the dichotomous variable has underlying continuum. Like when you say diabetic, yes or no, is you can code yes as well and no is 0. That's the dichotomous variable. It's a continuous dichotomous variable because it's blood sugar you did before. It's a continuous variable. You now have a cutoff anything greater than equal to 136 is diabetic. So there's an underlying continuous variable before you came about the diabetic, yes or no. The same thing with obesity. The same thing with hypertension. It's the same thing with anemia. All those things they have underlying it's just a form of correlation coefficient, but it's calculated the same way with person. Now, another question, so how can you differentiate effect side taught today and design effect? They are different because the design effect, that one, so we have a lecture on design effect. It's there on in our library. The video is there. The sign effect is effect you factor in because you are doing cluster sampling. You are doing cluster sampling. By doing cluster sampling, the people in the same cluster, they are likely to have the same attribute. So it's just like you are people in the same cluster. You say you sample 30 of them, you ask them question. Maybe you didn't ask more than 5. No, you ask all of them ask the question, but you have not got it. Those 30, they are serving as 5 or 2 because there will be similarity in what they tell you. So those 30 is just a number. So at the end of the day, you are not getting anything different as if you are getting different things from 30 people. That you are getting things different from 5 people. So because of that, you have to factor in so that you have to increase the sample size. If you don't increase it, you will discover that if you have sampled 300, it's like you are doing research for 100 people or 120 people because most of them similar thing they are telling you. So it's the design effect that will help you to know how much will I increase the sample size for me to get what I'm supposed to get. So it's different. So that was the effect of intra-class correlation. The sign effect is due to intra-class because in clustering they are intra-class correlation. That's great. So the person, it's the same person that asked the question that also asked the question about what is the definition of the growth. So the person should go and subscribe and go and watch all those things that are there. We have talked about them before. Then even when you stratify or multi-stage, some author know that there may be some design effect. Well, you say stratify. If you say stratify, it depends. Because if each stratum, there has similarity. Each stratum may be served as a cluster. But there are some things that may be similar. It depends on your research question. A stratum rather, may be a cluster for some particular variable. Yes. It's just like if you are studying people in university now. There are some things you will ask them. Imagine you are asking, when did you gain admission? It's the same thing for all the people that are in year 1. It's the same year for all the people that are in year 2, year 3. So there are some questions you may be asking them, the clustering effect may affect. So in that case, the stratum may be a cluster. But it's not in all the situation. It's a multi-stage. That one I can say because when you say multi-stage, that one is not even true. Because unless if you feel that multi-stage create a straight.
Should I explain? Should I explain how the multi-stage might happen? You know, if we use the classic one where we do local government, we do those levels we do. That's we start from local government to ward level 2. So if, for example, it's still tied to the type of variable we're looking out for. So if let's say you're looking out for, let's say you're trying to do a community nutritional assessment, and let's say some of the communities you're assessing, let's say there's a particular form of staple food. I'm just giving this as an instance that is predominant in that area. So it's still depending on exactly how you've explained, because it was something I read up. I didn't really know. I stumbled across a book online where they were like that. Sometimes some of those variables.
I'm listening to you. I'm listening to you.
Hello.
Who is? Please, if you want to be reciprocal, mute yourself, please. Yes. The issue there is that, well, you know why I will not agree with that? People can just speculate. Me, all these mistakes, my project, I've done a lot of it. In fact, they say when you do stratified sampling, it will help you. It's even more, is better than doing simple random sampling, because the logic they are talking about, they are trying to say, okay, this clustering effect, when you do cluster sampling, compare with simple random sampling. Yes, that one is true. But when you want to compare simple random sampling and multi-stratified sampling, stratified sampling is better because imagine you are studying people in a university now, where you have different levels. If you don't have initial and know the proportion of students in each level and try to say, let me divide my sample size for based on their proportion, and now use simple random sampling or whatever, or systematic or whatever for each level. You know, for each level, you have to use simple random or systematic random. It's not as when they say, actually, that's what I actually tell people. Even multi-stage, you say it's not a sampling. It's just a way, because by the time you there each stage, you are sampling each stage. Even the stratified sampling is actually a sampling method. It's just a way of making sure that when you are now doing the final sampling, you're able to spread out. Because if somebody now do stratified sampling, whatever they call it, the person is likely to spread. It will reduce clustering effect. But imagine if you don't do that. You just say, you stand at the gate, you are doing simple random sampling. That day, you may see more of a particular level. At the end of the day, when you finish, you discover that your sample is tilted to one level than the other. What will you do? So which one is better? The one that is well spread over the different levels and the one that is tilted to one level. Which one has more clustering effect now? Of course, the other one, the one that is tilted to one side.
Yes,
can you see now? The issue of multi-stage. What do you say? The issue of multi-stage.
Okay.
No.
The issue of multi-stage you are still talking about is to spread the people you are sampling over geographically, which is still the best. Because either you like it or not, if you don't do multi-stage, you just do, say you do this, you are likely to sample only one local government, only everything. If a particular thing is common there, will there not be clustering effect you are talking about? The multi-stage, what it does is for you to be able to spread out. Imagine now we are studying a state or a state. You now say you select 5 local government by simple random sampling. After that, for each one you select. So you have spread at least those 5 local governments selected is by chance occurrence. It's not that you just go and choose one, all of them, and they are in the same senatorial district. Or summer, you choose all of them, they are maybe more convenient, close to the city. So you will select your spread over, just by chance you have selected certain number. For each local government also, so that you will not concentrate on one side of the local government, you also you try to sample some wards. After that, you sample some streets before you sample household. So which one? Which one, even if there's going to be clustering effect, which one reduce it? It's the multi-stage. So sometimes, let me tell you something. Many people, they talk until they practicalize. It's not everybody, this to think mathematically is most difficult for some people. They can just come with one reason. When you come with one reason, unless you think very well, and you put it to even solve it mathematically, and now you go and work it to see if it will work or not. It's just like as I was preparing for this lecture, the issue of Cramer's V and Cramer's phi. Some people say that the Cramer's phi is from, they say it's correlation. Phi, they say it's correlation from -1 plus +1. I was searching. I wasn't convinced. I now got another one. Okay, just took it as Cramer's V. Okay, and then let me just. But as I went out as I was thinking, and I said, it's not even possible. You know why it will not be possible for it to even have negative? It's from 0 to 1 because how do you get it? You get it from chi-square over n. Chi-square cannot be negative because if you remember the way you calculate chi-square, even the negative when you square it cancel out. Because when you remove observed minus expected, the one that have negative, when you square, all of them cancel out. Because if the one that have negative oppose the one that have positive, if you add it together, give you 0. So when you cancel, you square, negative cancel out. That's why you cannot have minus as the chi-square. And this thing is chi-square all over n square root of it. Well, Can you have minor sample size? You cannot. So there's no even minus in it. It's not possible. So sometimes you need to reason. When you reason critically and you think very well. This thing you are saying, now that I've staggered about it, and now I've also staggered about reasonable people also that say, no, in fact, stratified sampling even is better in that sense. That's it. Why do you choose stratified instead of simple random? Simple random is only better in the place where all of them is homogeneous, one level. Yes, you can do simple random. But if you have strata, different strata, simple random will not, in fact, will even lead to that clustering. Because the people in the same level will likely have the same attribute. The same thing, if you refuse to do multi-stage, you enter the problem. So the issue about, yes, we know that if you choose a particular cluster or a particular local government, you saw you get a differ if you have chosen other. But for the fact that you cannot study the whole, you cannot go to the whole local government. And if you, for the fact that you studied, you choose that local government by chance, simple random sampling, yes, whatever different is by chance. That's just it. So people can come with many things. So yes.
The cluster sampling, I thought it's also by chance. That random selection of the clusters.
Yes, now it's by chance. It's by chance when you check around. It's by chance. But that is by chance that person, that local government is chosen because you do this simple. That's why they say is by probability. Now when you say probability sampling, is probability. Yeah. When you say sampling, it's not purposive. When you say probability sampling, you know that when you sample, you select based on all of them. They have certain chance of being chosen. So
exactly.
They have certain chance. If it's simple random sampling, they have equal chance. But if it is other apart from simple random, they have certain not equal chance. But in purposive, in all those things, there are some people they will not be chosen. So you already make up your mind. You are not going to have to reach area. So they have to reach area have no chance of being chosen. See, they are out of it. They don't even have chance of being chosen.
Okay.
Can you see now? So that's just it. So
yes.
Somebody even okay.
I was just saying.
Any other question?
I was just saying that because I know that the clusters. Okay, we will talk later.
What happened to the clusters? Today is I don't know why all of you are going to cluster. We discuss something else. All of you bring cluster. People should ask questions about.
Sorry.
You know all these clusters we have discussed them. So let us focus on what we are doing.
It was because somebody asked the question. That was why. Sorry.
So that you will not overshadow the lecture with cluster. About cluster, it has its own lecture, and you go and listen to it. You can now ask me a question later. But if we are discussing something else, any other one? Okay, no question. Many people are used to no question. Okay, no problem. Let me just stop the recording. Is somebody